I welcome all of you to the 9th tutorial. In this tutorial, we work out few problems with respect to the design, address mapping and working of DRAM as well as hard disk. The concepts that we have learned in the lecture videos will help you in solving these problems. So, I request you prior to attending this tutorial video, kindly go through the lecture videos of DRAM as well as the hard disk. The first tutorial question for the day is, let us consider a 32 GB DRAM system that uses 4 channels C0, C1, C2 and C3. It has 4096 columns per row. It uses 8 byte wide memory bus to transfer data from DRAM to the processor. If adjacent memory words are mapped onto adjacent memory channels, which channel which fetch the physical address that is been given. Let us try to understand what is the concept of channel. So, let us say this is the processor. Now, your memory is connected through 4 channels, that is the meaning of this. So, here we have different DIMMs in DRAM, and these 4 channels basically means there are 4 point of entry from the DRAM system into the processor. So, this permits us to parallelly access 4 memory locations provided they are from different channels. So, in this 32 GB DRAM, so 32 GB that corresponds to 2 power 5, that is 32 into giga stands for 2 power 30. So, we have 35 bit address. Now, this 35 bit address whatever we are talking, that has, now it is telling there are 4 channels. So, some of the bits, then there are 4 channels, 2 bits somewhere in the address will tell you which is the channel this particular address is mapped to. Now, this has 4096 columns per row and it uses 8 byte wide memory bus. So, when you bring something from the DRAM into the processor, its 8 byte is coming together. These are 8 continuous bytes in the memory. So, the last 3 bits in the address, they belong to 8 continuous bytes. So, whatever be the most significant 32 bits, you keep them constant. The last 3 bits only if you vary, these are the bytes that are brought together in one fetch. Now, if you are telling, so this is what is called a word. So, these 8 bytes constitute your one word. The peculiarity of the address of the bytes within a word is they all have the address. The most significant 32 bit of the address is same. The bytes of a single word will differ only in the last 3 bits of the address. Now, if adjacent memory words are mapped onto adjacent memory channels. So, adjacent word means, let us say this is one word, the very next word will all these be same except this bit, that is immediately before the last 3 bits. That is a word that will differ, that is called adjacent word. If adjacent words are mapped onto adjacent memory channels, so these 2 bits will be your channel bits, such that the adjacent words are being assigned to adjacent channels. So, given in this address, this is the address that is being given. Let us take 4 2. Now, this 4 if you write 0 1 0 0, this 4 2 is the last 8 bits. Now, 2 is 0 0 1 0. Now, these are the last 8 bits, out of which the last 3 bits will be part of byte within a bus, and it is these 2 bits that will tell you which is the channel. So, this indicates that this particular address is mapped to channel number C0 that has been given in the question. Let us now move into the next question in DRAM address mapping. Consider a 64 GB DRAM system organized as 4 channels, each channel with 2 DIMMs, each DIMM having 2 ranks. The system uses 8-bit chips and 8 banks. Each bank has a collection of byte cells which can store 8 bit of information organized as row and column. That is, the meeting point of row and column is a byte cell. The bank configuration is in such a way that the number of rows and columns per bank is equal. The system uses 8 byte wide memory bus to transfer data from DRAM to the controller. Each channel is connected to 16 GB of continuous memory. Let us try to rephrase what are the things that is been given in the question, the important points. So, in this case, it has been told that we have a 64 GB DRAM, 4 channels, 2 DIMMs. Since it's 64 GB means 2 power 6 into 2 power 30, that is 2 power 36 is the number of bytes. You require 32-bit address. So, 64 GB is you require 36-bit address, 2 power 36 bit. So, 36-bit physical address is there. Now, these 36 bits we have to divide into channel, DIMM, rank, bank, row, column and byte. Now, it's an 8-byte wide memory bus. Like in the previous question, the last 3 bits in the address will represent byte within a bus. Is used to transfer from DRAM to the controller. Now, each channel is connected to 16 GB of continuous memory. When you have channels wherein the 16 GB of continuous memory are part of the same channel, so it is a first 16 GB is one channel, next 16 GB, third 16 GB and the last 16 GB, together they make out 64 GB. So, if this is the organization, they should have differ only in the most significant bit. If the most significant 2 bit is 00, it is a first channel, then 0, 1, 1, 0 and 1, 1. That is why the first 2 bits are channels. Now, let us say we have 2 DIMMs. So, somewhere 1 bit is there for the DIMM and generally it will be there the most significant bit immediately after the rank. And we know that DIMMs are further divided into ranks. So, we have 1 bit for rank, we have total 2 ranks. So, 1 bit DIMM and 1 bit rank. And then we have 8 banks. So, somewhere we have 3 bits inside the address. So, this location of the bank is still not sure for you. Anyway, there are 3 bits that is been reserved for the bank. So, out of 36, we have 3 bit for the byte within the bus. That is what this is talking. You have 2 bits for channel, that make it 3 plus 2, 5 bits is already gone. And then we have 3 bits for bank, that make it 8 plus 1 bit each for DIMM and rank. So, out of total 36 bits, already 10 bits are gone. So, remaining you have 26 bits. These 26 bits I have to split into rows and columns per bank. Now, it has been mentioned that the number of rows and columns per bank is equal. So, the remaining 26 bit whatever we have, I will divide into 13 bit row and 13 bit column. That is what is been given. Now, if the system is using row interleaving, so this row interleaving will tell you where you have to keep it in the bank. Which bank the physical address 0x844332255 is mapped to? Which channel serves data belonging to this address? There are 2 questions. One is which bank this address is mapped, second one which channel it is been mapped. Now, how will you find out bank? So, since you are using row interleaving, we have to find out where the bank locations are there. Row interleaving means adjacent rows are mapped to adjacent banks. So, you know that you have rows and columns. So, once all combinations for the column bits are being given, then we are going to change the row. So, once you completing of a row means you have given all combinations of columns. So, it is after the column bit. So, when you apply row interleaving as discussed in our lecture video, the bank bits will come in between row address and column address. So, these are the 3 bits for the bank. And we know that the most 2 bits, the most significant 2 bits that is being given to channels. So, given the address 844332255, you know that the last 16 bit is gone for column number and byte. So, I am removing the last 16 bits, that is not interest of to me. The next 3 bit, so this represents a 4 bit 3. So, the binary value of 3 is 0011, out of which you take these 3 locations. So, that will tell you 011. So, that means that this particular address is mapped to bank number 3. So, let us try to conclude what we do here. Given the address, we find out what are the bits for channels and banks. Since it is row interleaving, the bank bit should be in between row and column. So, you have to extract these 3 bit from the given address. So, this is a 36 bit address, out of which these 3 bit is of interest to us. So, we remove the last 16 bit, take off the next 4 bit that defines 0011. From that, you take up the 3 bit, that is bank 3. Now, if you wanted to look at the channel, it is a most significant 2 bit. So, the most significant hex that is been given is 8. 8 means 1000, and this is the most significant bit, that tells that it is channel 2. So, this particular address is mapped to bank 3 and then channel 2. Similarly, for the same question, if the system uses a 128 byte last level cache and is using cache block interleaving in banking, which bank the physical address 0x22446668AA is mapped to? So, here we are bothered about 128 byte last level cache. This concept also we learned in our lecture video. So, we need to carry 128 bytes together because you have to fill up the last level cache. Generally, data from the DRAM is being copied to last level cache. So, this 4 plus 2, that will give you 7 bits and that will give you 2 power 7. 128 bytes means you keep all these locations same address, you vary the last 7 bit, that will give you 128 bits that are to be 128 bytes that are to be transferred from the DRAM onto the way to the last level cache. So, since you have total of 13 bits in the column, out of which only 4 bits are used here, so your column bits get separated and the bank bit will come in between your column. So, why this separation happens here? Because I require total of 7 bits at the end. So, adjacent cache blocks are mapped onto adjacent banks. So, this is the 3 bit of your interest. So, when you take this, the address that is been given, these are the last 12 bits. I write the last 12 bits, out of which 7 is being extracted. The next 3 bit will tell me which is the bank. So, we are working with bank number 1. This question is about raw buffer management. In a DRAM system that follows open raw buffer management policy, which of the following sequence of commands are generated if the new request is to a different row from the row that was accessed last? So, we have to see it is a open raw buffer management. So, here we have a bank wherein you have rows and columns, you have the raw buffer. Now, we have a queue. This is in the DRAM controller, we have the queue of request. So, in a DRAM system that follows open raw buffer management policy, which of the following sequence of commands are generated if the new request is to a different row? So, I got a new request, this is totally different. Let us say this is part of row number A and now we have row number B that is there in the raw buffer. So, raw buffer carries one row, the new incoming request is to a different row. What we will do? So, in this case I have to store the contents of B back into the corresponding row. There is one signal and that signal is known as pre-charge. And then you have to activate the new row. Let us say this is the row corresponding to A. So, we have to bring it back. So, it is activate. So, in this context the answer is pre-charge followed by activate. So, activate alone means if the contents of a particular row is transferred to raw buffer. Pre-charge means contents of raw buffer is transferred back to a row. Activate followed by pre-charge, that means you transfer something into a row and then you transfer something into the raw buffer and then you store it back from the raw buffer into the row. That is not relevant here. So, pre-charge is what is been to be done first followed by the activate signal. Next one is also a raw buffer management question. For a sequence of memory requests coming to a particular bank at regular intervals such that every request reaches the scheduler when the processing of the previous request is in progress. Which of the following holds true for FRFCFS scheduling? So, there are 4 statements given. Open page policy gives lesser average turnaround time than closed page policy. Closed page policy gives lesser average turnaround time than open page policy. Closed page policy gives less average starvation than open page policy. Both open page and closed page policy give same average turnaround time. And we cannot compare open page and closed page in this context with whatever given details. So, we have to understand what is the concept of turnaround time. So, when you have a request that is coming into the DRAM queue, that time onwards until the request is being completely serviced, that means the content that is being asked by the request is being transferred to the DRAM controller, that is called turnaround time. So, you have a bank which has a raw buffer and now some contents are existing there. Now, we are in the process of extracting the data. So, every new request is coming to the queue in such a way that prior to the completion of this previous operation that is being under service, new elements are coming. Meaning at the end of the operation, there have some elements already in the queue. Now, what is the difference between an open draw policy and a closed draw policy? In the case of an open draw policy, after servicing a request, we keep the row open, hoping that the future request will be to the same row. So if the future request is to a different row, then you have to do a pre-charge and then activate the new row. If it is a closed row policy, by the time you complete the servicing of a given request, if the queue is empty, then we don't know what is going to come in the future. So you perform a pre-charge operation, hoping that the future request that is going to come is to a totally different row. So in open row policy, we hope that the future request is to the same row, leaving the row open. In closed row policy, we hope that the future request will be to a different row. So there is no point in keeping the row open right now. Let me close it. That's called pre-charge. Now in this context, in the given question, we have always your buffer occupied with some request. There won't be any case of the buffer empty. That's what is being told. When the previous request is in progress, or processing of the previous request is in progress, the new request is coming. So the new requests are always coming when the previous one is in progress, means when the previous request is completed, we don't have an empty queue. If you don't have an empty queue, then in the case of an open row policy, we can search for FRFCFS scheduling, whether there is anything to the same row. If so, apply only CAS. If it is a different signal, perform pre-charge and then activate. In the case of closed row also, as long as you are applying FRFCFS scheduling, first ready, first come first serve. If at all you find anything row buffer hit, try to pick up that request in the queue. If you are not able to find out, anyway you have to activate a new one, so it's pre-charge. So both row buffer management policy and closed row buffer management as well as open row buffer management are going to be picking up requests in the same order. So there is no difference at all. So the answer is the turnaround time is going to be same in the case of both open row and closed row policy. So this is what we are told. So we have always, whenever we are progressing something, we have a queue and the queue is non-empty. As long as the queue is non-empty, open row policy and closed row policy won't make any change at all. So both open and closed row policy will give same average turnaround time. Let us now come to a scheduling question in DRAM. A DRAM controller is using a closed page row buffer management policy. Assume that it takes 20 cycles for a row to be transferred from the storage array to the row buffer after the activate signal is enabled. So once you give an activate signal, it takes 20 seconds for the data to reach row buffer. And then it takes 10 cycles for the data to move through data bus to memory controller after the CAS column address drop is enabled. Minimum 15 cycles are needed between a pre-charge signal and an activate signal. The controller is using FRFCFS scheduling algorithm. Consider the following 10 memory requests that came to bank 2 of this DRAM controller. So you are going to get few requests, all of them are to same bank, so we are dealing with only one row buffer. Now the way in which the requests are represented is Rx, Cy and TZ, which represents a request arrived at the Zth clock cycle, the last entry is the clock cycle, for a word at row X and column Y of bank 2. So this means row 15, column 78, the request came at time 10. Row 20, column 50 at time 20. So you have a sequence of requests. Now we are supposed to know what are the time in which these signals are being applied, or by what time you can complete the operation. So these are the important things from question. It's a closed row buffer management policy. So as long as, so when you complete servicing a request, if the queue is empty, then you will pre-charge. That's the meaning of closed page row buffer management policy. 20 cycles between an act and a CAS, 10 cycles between a CAS and transfer of data, 15 cycles between a pre and an act, FRFCFS scheduling algorithm. So what we do is, let us try to organize the given data. Whatever data is been given, we are going to write it as row number, column number, followed by the time at which it is arriving. So if you look at the very first data, first one is R15, C78 and T10. So R15, C78 and T10, time is 10. The second one is 20, 50 and 20. So at time 20, that is the third parameter, in row number 20 and column number 50 we have the data. So I am organizing the data in the order of time of arrival, and these are the rows and columns. Now let us try to understand. Initially the row buffer is empty. Now when you look at time 1, there is nothing there in the queue, at time 2 there is nothing. So the first element reaches only at time 10. As and when it reaches, we have to schedule it. So we will give an activate signal, because already the row buffer is empty. So when you give an activate signal, it takes 20 cycles for the data to reach corresponding row buffer from the row. And then, so it takes 20 more cycles. So at time cycle equal to 30 only, the data is ready in the row buffer. Then you apply a cache signal, it will take another 10 more cycles. So the transaction is complete at clock cycle 40. Now in clock cycle 40, if you look at, these are the two requests that have already reached the scheduler. So if you look at that, one is to row 20, other one is to row 24. So my scheduling is FRFCFS. The current row that is opened is 15. So there is no other request that is there in the queue which is to the same row. So the ready concept is not there. FRFCFS, first ready. No other row is ready. So we have to go for FCFS policy. So out of these two requests, it is this request which came first. So I am going to do that. How will I do? So at 40 my previous one got over. So at 40 I am performing a pre-charge by which row number 15 which was there in the row buffer is written back to the corresponding row. At 40 I generate a pre-charge signal. It will take 15 cycles to complete the pre-charge operation, making the time by 55. Then I have an activate which will take another 20 more cycles. So at 75 I can give cache, 10 more cycles. So at 85 I will complete. So at 85 if you look into, these are the two elements that are already there in the scheduler queue. But we see that one is to row 24 and the other one is to row 20. So even though the request which came late at clock cycle 80, it is to row 20 and column 78, whereas the request which came at clock cycle 35 is to row 24. Currently the time is 85. So these are the two elements from which one I will pick. The first one, even though it reaches first, it is to a different row. The second one, it is to the same row. So as per our policy, whenever we are able to service a request that is to the same row, we have to do it first. That is called FRFCFS. So now, rather than the third one, it is the fourth one that gets scheduled first. So here we have to apply only a cache signal. At 85 we complete the previous one, 85 you can apply the new column. Why it's new column means previously I serviced to 50, now the request is to column number 78. So just give only column number, in another 10 cycles you are completing. Now the peculiarity is at clock cycle 95, we are completing the transaction with respect to the third request. Now we have to go to the new one. So at 95, at clock cycle 95, which is the one that is pending, only this is pending. So there is no other way, we have to pre-charge it. So that's the fourth one, we pre-charge at 95, it takes 15 cycles. So at 110 pre-charging is over, generate the activate signal, it takes 20 cycles more. At 130, activate is complete and the data is ready in the row buffer. We generate cache signal at 130, by 140 it is over. And then the transaction is complete at clock cycle 140. Now what 140, we don't have any other request. The new request is coming only at 150. So at 140, we don't have any other request that is been there. It's a closed row policy. So we hope that in future, whatever request that is coming is to a different row. So at 140, what I do is, I am doing a pre-charge operation, which will be taking time up to 155. So even though we have a request at 150, we can start the activation only at 155, because at 140 we have given a request for a pre-charge because it's a closed row policy and it will get over at 155. So at 155 act is given 20 cycles, 155 plus 20 175, another 10 more for cache. So by 185 the transaction is complete. If you look at 185, what you have left? You have only one request that is been left, and that is to a different row. So there is no other way. At 185 you are giving pre-charge, and then you are giving an activate at 200, 220 cache, and 230 the operation is over. By 230 these three requests are already there. So we have to understand that this is now row number 24. If you look at the remaining three requests, one which came at 200, other which came at 210, and the third one which came as 220, this one is to the same row. So as per the policy, I will service the one that is having a hit. So the seventh one that is been serviced is this one. So we have to apply only cache at 230, by 240 it gets over. Now by 240, these are the two ones that are already there, out of which none of them is to same row number 24. So you go as per FCFS policy. So that makes this request that is to be serviced. At 240 you give pre-charge. So, you are completing a transaction at 240, at the same cycle pre-charge is been given, 15 cycles activate is given, 20 cycles cash is given, 10 cycles at 285 you complete. So, by 285 what we have is we have these two elements also ready. Now, currently I am processing row number 35, none of them is to same row. So, you give which one came first. So, one which came at 210, that is been serviced with the timing 285 for pre-charge, clock cycle 300 for activate, 320 for cash, and 330 the transaction is over, and then you have the last one that is getting serviced. So, the whole thing will get over at clock cycle 375. So, now it has been asked what is the order in which it has been serviced. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. This is the order in which the requests are getting serviced, and these are the clock cycle in which the DRAM controller receives the data, and these are the times at which pre-charge, act and cache everything is been done. So, in this question what is given is we have been given a set of requests that is been coming to a particular bank of the DRAM controller, and now we are trying to find out what are the order or what are the timings at which various signals are being given. So, as far as DRAM is concerned, the time at which the signals are given is very important. So, as mentioned in the question, after you give an activate signal, it takes 20 cycles for the data to reach the row buffer from the corresponding row. So, the cache signal can be applied only after 20 cycles. The circuitry of the DRAM has to be designed in such a way that these timing constraints are to be strictly followed. So, this gives us a different picture of how, even though the requests are coming in an order, the way by which they are being serviced is based upon the scheduling algorithm. So, FRFCFS is the most common scheduling algorithm that is being followed. When you are done with the request, look into the queue, what are the set of requests that is been available, and pick up that request which is going to have an exact row match. The row number of the incoming request is same as the row that is been currently kept open in the row buffer. If you are not able to get a match like that, then you go as per FCFS scheduling. This is the way in which it has been done. I request you to practice few more problems in this to get more clarity as far as the timing and the signal generation of DRAM controller is concerned. Now, let us move on to the hard disk. This is a question with respect to cylinder skew. If a 6000 RPM disk has 256 sectors per track and the track seek time is 780 microsecond, what is cylinder skew? So, what is basically cylinder skew? Offsetting the start sector of an adjacent track to minimize the likely waiting time when you switch on to the tracks. So, this is the cylinder. Let us say you can see that here we have 1, that is sector number 1 of a track. But if you look into the sector number 1 of the next track, it is not exactly in the same line, it is been shifted. Sector number 1 of the next track is shifted, sector number 1 of the very next track, like that if you look into the sector number 1 of various tracks are not exactly in the same line, they are being slightly positioned. What happens is when your head is now currently touching sector number 1 and go all the way read the data up to sector number 31, now you want to take the data from the very next cylinder. So, the head is going to get itself detached from track 0, let us say here, and then it is moving to the next track. By this time, since the disk is rotating, by the time you take off from track number 0 and come back and touch down track number 1, some of the sectors have already slipped. So, to avoid that, sector number 1 or 0, whatever is the beginning of the sector of the next track has to be slightly adjusted or shifted such that during this takeoff and landing time of the head, you are not going to lose your data. So, it is actually a 6000 RPM disk. That means the disk is going to rotate at 6000 times, it is going to revolve around the axis in 1 minute. So, 6000 revolutions you are going to make in 60 seconds. That means one revolution will take 60 divided by 6000, that is going to be 10 millisecond, 60 seconds divided by 6000. So, it takes 10 millisecond to complete one rotation. Now, it has been mentioned that you have 256 sectors. So, completing one will take 10 millisecond. So, during this 10 millisecond, you are moving across 256 sectors. So, how much time you are going to spend on one sector? Roughly 39 microsecond you are going to spend on a sector. So, if it requires 10 millisecond to cover up one complete track, that means 256 sectors, approximately 39 microsecond is what you spend. So, 10 millisecond divided by 256, it is 39 microsecond. Now, it has been given in the question that track seek time is 780 microseconds. So, that is you are going to take off from one of the track and then going to touch down the very next track. So, during this time, so that is the time given, track seek time. It takes 780 microseconds to switch off from one track and touch the adjacent track. So, during this 780 microseconds time, you actually pass through 20 sectors. So, 20 sectors have already gone by the time you touch down. So, in the adjacent cylinder, the next sector has to be squeezed or shifted by 20 sectors. That means, here it is 1, the one of the next track should be kept at a distance of 20 sectors. So, somewhere here, then here, like that. This is the way how cylinder skew is being calculated. So, computation of cylinder skew will help us in finding out how much should be the shifting that is being done in adjacent cylinders as far as numbering of the sector is being concerned. Then there is yet another important section as far as disk is concerned, that is about scheduling. Given a series of requests, you have to find out what is the order in which they are scheduled. We have learned different scheduling algorithm like FCFS, SSTF, shortest seek time first, scan algorithm, look algorithm, then the elevator algorithm, like that. Already during the lecture session, we have taken one example and found out what is the average turnaround time and waiting time of all these. So, when you get a sequence of request, the request can be of the form platter number, track number, sector number and all, but as far as scheduling is concerned, what we want is only track number, which is eventually the cylinder number. So, scheduling is done with the help of cylinder number. So, from the given set of requests, extract the cylinder numbers alone and then based on the cylinder number, apply the algorithm whatever being asked. So, since already we have discussed with the scheduling algorithms with numerical problems itself during the lectures, there is no specific question that is been planned as far as tutorial is concerned, but kindly work out maximum number of questions. So, by this we have almost come to the penultimate week of this course. I hope you are now preparing for the final exam as well. Kindly do go through all the videos that is been given and these tutorial sessions where numerical problems are worked out, which will give you more grip on the topic. And kindly do prepare well for the final exam. We have just one more week that is been left. Thank you.